let me tell you why this blunt is good for your health. One of the things I was told many times when I first started trying to learn about lightning protection systems, and came up in the comments of the last video, was make sure to use a fine-tipped lightning rod air terminal. I've also seen they kind of look like those, historians apologize, those like Roman or Greek, like those feathered thingies where you have a metal rod that goes up and it's like a fan of little bristles. Both of these were supposed to be better at acting as lightning rods. Both of them won't work. For those of you who just want to get to the meat of it, here's the TLDW. The fundamental reason why blunt tips work better is that pointed tips, I thought I had a pointed tip thingamajig. I don't have anything pointed to use as a prop, so just pretend this is like, a needle. The problem with a fine point is that it is going to send up its streamer too soon. As the cloud that is going to send the lightning strike that's going to hit your boat gets closer, it's generated a large electric field, and that electric field is having more and more influence on your boat. Exactly what that means will be what the majority of this video is about, but for now, take that as truth. At some point, the air terminal is going to send up its own electric streamer, and a lightning strike happens when the streamer sent up from the ground connects with the stepped leader coming down from the cloud, closes the circuit, creates a plasma channel, which is a very low resistance wire, and the current flows, and all the smoke happens. So the conventional logic was, if you have a fine tip point, it is going to send up a streamer easier, and so have a better chance of sending up the streamer that connects to the lightning bolt. However, starting in 1983, a scientist named Dr. Charles Moore started working on research where he theorized that a blunt tip would act as a better air terminal than a pointed tip. He did research where he created entire fields of air terminals. I think it was in Mexico, where he had pointed tip and blunt tipped air terminals spread out, and he counted how often they were struck. In all of the time of the research, not once did a pointed tip get struck. It was always the blunt tips that got struck. Why? His theory, which proved to be accurate, was that the fine-tipped pointed air terminals sent out its streamer too early. And what ended up happening is, as the streamer started to form, it would start to strip the electrons, well, strip or pack depending on the polarity of the strike, but I'm going to say strip. It would strip the air molecules near the tip of their electrons, which would make them take on the same charge as the metal itself. So a positive charge in a standard negative cloud to ground strike. And that little buffer of air acted like an insulator, like a shield. The reason it acted like a shield is that the air was about 1,000 times less conductive than the air terminal. So while it would start to send up a streamer, you would start to see that St. Elmo's fire, you would see that plasma discharge, that coronal discharge. It would not actually connect to the cloud, and instead, something nearby, like your weather station, your VHF antenna, would instead, something blunter, would send up the streamer that actually connected to the step leader, and the whole purpose of having a lightning rod was defeated. He first published his paper in 2000, and then he had a subsequent one that he published in 2003. Links in the description. His paper was so conclusive that the standards bodies changed from then on to say you should have a blunt tip. So for those of you who are old salts, who've been around for a long time, or who were taught by people who've been around for a long time, the advice that you were given to use a pointed tip was correct before 2003. What replaces science? Better science. And that is why a blunt tip is good for your health. So now for the rest of my nerds, let's dive into the details of why the blunt tip sends up a streamer later and has a better chance of connecting to the step leader, and for this thing to actually do its job. So as I've said in many other videos, I am not an expert. I have no training. I am not educated. I am just a random person on YouTube. I'm going to do my best to explain this, but I might make mistakes. So if you're interested in the details of this, consider what I'm going to say a starting point and a potentially flawed one. So to understand how the lightning rod works, we need to make sure that we have a good foundation on how lightning happens in the first place. And even before that, let's take a moment to talk about charge. This is something that confused me for a while until I realized a negative charge has an excess of electrons. A positive charge has a deficit of electrons. This comes from the fact that I think it was in the 1740s, Benjamin Franklin, when he was first trying to understand electricity, he envisioned it as a type of fluid. Now, this was 150 years thereabouts before the atom as a thing was discovered. And because of this, he was guessing which way the charge went. It was a 50-50 guess, and he got it wrong. By the time the science advanced enough that we understood the atom and we understand the direction of charge transfer, the math and 150 years worth of literature had already established what we now call as conventional current. And this is where, when we say there is a positive charge, like the plus on your battery, it travels to the negative side, the negative terminal on your battery. That's actually backwards. However, the physics and the math work out that it might as well be correct, and so it's left alone. Now, with that said, let's talk about how the charge happens in a cloud that leads to the lightning strike. The weather that leads towards a cloud, a cumulonimbus cloud, that is going to generate a lightning strike, starts with warm air rising up. The warm air rises up until it hits the top of the tropopause, which is about 9 to 15 kilometers up in the air. The cloud doesn't start that high, it ends that high. So you end up with these big pillowy clouds that we know as cumulonimbus clouds. The air that's traveling up through these clouds is going extremely fast, over 100 kilometers an hour. Inside of the cloud, there are three things that are relevant to what we're discussing. There are ice crystals, there's Graupel. Graupel is the name for a type of porous, spongy hail that is suspended in the cloud. Graupel is significantly larger than ice crystals. And the third one is supercooled water. This is water that has gone below 0 degrees, but because there was no crystal or nucleation point to turn it into a solid, has stayed a liquid. The rising air, that high-speed rising air, carries the relatively small and light ice crystals upwards, and they collide with the relatively stationary Graupel. When these collisions happen in the presence of supercooled water, a charge transfer happens. For those of you who understand this already, you're going to point out that the charge transfer direction is dependent on temperature. You are right. I am going to discuss the charge transfer happening so that the positive charge goes into the ice crystal and the negative charge goes into the Graupel. And then this positive charge is carried up into the tropopause, up into the anvil of the cloud. This always happens below minus 20 degrees Celsius. Above minus 10 degrees Celsius, the charge transfer can go in reverse. The only thing I'm going to say right now is just to keep in mind that we're going to talk a lot about negative cloud-to-ground strikes and positive cloud-to-ground strikes, and how positive cloud-to-ground strikes are much more intense because they start up at the tropopause, up at the anvil of the cloud, so they have to jump a much larger distance. So by the time the charge is large enough to create a positive cloud-to-ground strike, it is incredibly powerful and destructive. The caveat to that is that you can have a low section of the cloud that is positively charged because of this high temperature, relatively speaking, reverse charge transfer. This is a level of detail that's just going to confuse things, so there it has been said. Please don't write it in the comments, or do, engagement helps. For the rest of this though, we're going to assume that it is always the cold below minus 20 degrees Celsius charge transfer scenario. When the ice crystal strikes the Graupel in the presence of supercooled water, the supercooled water splits from H2O into H plus proton and an OH negative, a hydroxide ion. You have on the one side an H plus proton, which is the positive charge inside of the atom with no electron whatsoever. That goes to the ice crystal, giving the ice crystal a positive charge, a deficit of an electron. The OH negative, which has the extra electron, the hydroxide ion, goes into the Graupel. And because of the high speed, the ice crystal, which now has a positive charge, goes flying up into the air, and you have this Graupel, which now has a negative charge, an excess of electrons, or an excess electron. This is how the charge starts to build inside of the cloud. This is happening, I'm going to say billions and billions because Carl Sagan is awesome and that's a Sagan. This happens a Sagan of times inside of the cloud, and it causes the body of the cloud to have a growing negative charge. It is growing its number of excess electrons. Up at the anvil, at the top of the cloud, you are having a buildup of a positive charge. This is what leads to the positive cloud-to-ground strike that I mentioned earlier, and I'm not going to go into any further now. So the body of the cloud is developing a stronger and stronger negative charge. Okay, now we understand how the charge builds up in the cloud. How do we get this back down to the boat and the lightning rod? For that, we need to understand electric fields. When you have a charge starting to build, that charge generates an electric field, and the strength of that electric field, and thus the range of the effect of that electric field, is dependent on the strength of the charge. So as the negative charge builds and builds, the electric field gets stronger and stronger, and its reach gets further and further. Now recall, the body of the cloud is not what is 10 to 15 kilometers up, it is much closer to the ground. This field is growing and growing and growing, and eventually that field is going to reach the surface of the Earth. Though, being at the water, it's going to reach the surface of the water. If our boat happens to be bobbing along, it also reaches our boat. When this negative electric field reaches the boat, which is the part we're actually concerned about, so we're going to put aside the water for a minute, something happens. That negative electric field is going to be a repulsive force on the electrons in the metal of our boat. If you were like me and you were taught in grade school last the structure of an atom, it was often presented as being somewhat similar to a sun with a bunch of orbiting planets. So first, you have your electron shell. That is the outer layer of electrons called the valence shell. And then inside of that, you have lower layers. How many layers, how many electrons per layer, depends on the metal and the atoms involved. Those inner layers are tied relatively strongly to the nucleus of the atom, and the outer layer is much more free to move. Now, the reason I mentioned how we were taught the classical understanding of atoms, that their electrons are these little bodies like mini planets that are just like orbiting around the atom's core, that is not accurate. We're getting into the realm of quantum mechanics, and I think it was Feynman who said that if you think you understand quantum mechanics, you definitely don't understand quantum mechanics. I'm not even going to try to explain it, and I certainly don't understand it, but the part that matters can be easily understood, and that is that the electrons are in a probability cloud. If you actually try to measure, classic two-slit experiment, the position of an electron, you collapse its waveform and it acts like a particle. But when you're not observing it, it acts like a wave. For the sake of this discussion, we are going to talk about it for now as if it's a particle. So if we assume that this thing is made up of pure aluminum, which it isn't, but let's just say that for now. You have in here a matrix of aluminum atoms in a crystalline structure. And that is a rigid bond, it's like a cubic shape of aluminum atoms connected to each other that form the metal body of this rod. It's the same for copper and other conductors, but I'm just going to stick with aluminum because that's what I have in my hand as a prop. So you have this lattice work, and on the surface of this lattice work, you have a sea of free electrons. That is the electrons in the outer valence shell of the aluminum atom. They move about. So if you wanted to look at any individual electron, it is just sitting here moving freely around the surface of the metal. It's not bound to any one particular atom. So you have this negative electric field now that is coming down from the cloud, which again came from a source of excess electrons. Like repels like. So you have this electric field interacting with this lattice work of the aluminum and this sea of electrons, and it wants to repulse some of those electrons because a negative charge and a negative charge want to get away from each other. The ability for an electron to resist the cloud's electric field is effectively zero, so it's going to get pushed down away from the surface of the metal. What ends up happening then is that if you look at how many atoms you have, and the atom's nucleus is positively charged, Now that you've lost that electron, a little bit of the overall positive charge of the metal latticework is now being exposed, creating a tiny positive electric field. Now, if you lose just one electron, who cares? But as the field grows and grows and grows, more and more electrons are going to be knocked down from this sea, exposing more and more of the positive charge innate to the latticework of the aluminum atoms that make up your actual rod. As more and more electrons are stripped, the positive charge is growing and starts to generate its own field, its own positive electric field. What determines how many electrons get knocked free? So the strength of the negative electric field coming down from the cloud is going to drive away a set number of electrons. And that total number of electrons driven from the surface is going to result in the total charge potential of all of the metalwork on your boat. That is going to set the system voltage potential. What that overall charge translates to depends on the geometry of the metal. And now we're getting closer to why you want a blunt tip. So understanding that the voltage potential of the system is the sum of all of the knocked free electrons or pushed down electrons, we need to now take a look at what resists those electrons being pushed down. And it's fundamentally two forces. The first is this sea that I was talking about being on the surface of the metal is actually all through the metal latticework. So as the electron is pushed down, you're now generating a negative charge deeper in the metal, which is going to put an opposite repulsive force on that electron, pushing it back towards the surface. Simultaneously, as the electron gets pushed down and the positive charge above it starts to grow, that's going to act as an attractive force, trying to pull it back up. So you have a combination of these two forces that are trying to pull this electron back up. This is where the geometry starts to matter. So if I have an absolutely flat surface, I have two things that are now working on the electrons that are being pushed down. I have an equal number of electrons pushing from all sides, trying to pop that thing back up, and up above, I have now the positively charged atoms reaching down and pulling it up from all angles. So the total force pushing that electron back up is fairly strong. Now, if I start to curve the surface, the number of electrons down below starts to reduce, making it easier for an electron to get pushed down. Imagine that we're on an aggressive part of the curve here. An electron at this point in the curve is going to be pushed down, and because there's physically less material on one side of it, there's less electrons pushing it back up. Simultaneously, there's less positively charged exposed aluminum atoms pulling it back up, meaning it gets a lot easier to push the electrons down. The result is that anywhere where you have a tight radius, you have an excess of lost electrons, resulting in an increase in the positive charge. This positive charge generates its own electric field, as we mentioned. Now, it's important to say that at the atomic level, no matter how sharp something is, it's not a perfect point. It is still, if you could look at it with a strong enough electron microscope, you would still see a curve, a radius to the tip. So understand that no matter how sharp the tip is in practice, it is still a radius. As the tip gets more and more pointed, as the curve of the radius gets tighter and tighter, the number of electrons that'll get pushed down by the electric field goes up and up. This is exacerbated by the fact that the tip is bound to the rest of the metal of the boat, because this gets screwed into the mast is connected to everything else, and, well, okay, it's going to get into a little bit of detail with my boat, but assume that the lightning electrical system is bound to everything else on the boat, you have a lot of horizontal metal. This horizontal metal on the boat has a lot of surface area exposed to the negative field coming down from the cloud, which is going to raise the overall system voltage potential. This is going to act to further reduce the ability for the tip to resist the electrons being pushed down, because the electrons are going to be drawn down trying to fill the gaps of those missing electrons along the flat surfaces. So you have multiple forces causing the charge at the tip to get stronger and stronger. Okay, now we're getting closer to why this actually matters to the lightning rod. So we now understand that the deficit of electrons at the tip is going to be higher because of three factors. You have the overall voltage potential is going to make it easier to draw those electrons out, and the radius of the tip means that there's going to be less aluminum atoms who have a positive charge to try to pull those electrons back up, and there's less electrons down below pushing those electrons back up. So the tip is going to get a higher and higher charge. So as the positive charge builds at the tip, it creates this very strong positive electric field. And as this positive electric field interacts with the air atoms around it, the air molecules around it, it hits a critical point where it starts to strip the electrons off of the air and draw them down into the metal because it's so desperately trying to fill those gaps. When this starts to happen, you see the coronal discharge, the St. Elmo's fire, this glow that you see coming off the tip of metal in highly charged environments. So now we get back to what I was saying earlier about how you can end up with a buffer around the tip. So as it starts to send out that coronal discharge, it is stripping the electrons off of the air molecules around the tip, making the air itself positively charged. By the time you see the coronal discharge, the St. Elmo's fire, the air has already been driven to a very high positive charge, and it's acting as a space charge. And the space charge is the shield that prevents the stepped leader from contacting the tip and actually turning this into the conductor for the current from the lightning strike. Now we can put the final piece together, and that is, we need to time when the streamer leaves our lightning rod so that it makes contact with the step leader before the space charge, that insulator, can form. So the blunt tip is all about timing. By having the radius, what you've done is it's acted like, what's that movie where it's like, hold, 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 and everybody's like ready to fight, and then go, and then it, blah. It's kind of like that. You have the positive field building and building and building, but it doesn't hit that critical breakdown point where it would actually send up the streamer until the stepped leader is very close to the tip. So that when it does send up that streamer, it connects with the step leader, forms the circuit, and pulls the current down through the rod, which gives us our ability to control the path of the current. Again, if you are really interested in the physics of this, take this video as just a starting point. Again, I cannot stress enough, I am not a scientist, I am not an engineer, I am not an electrician. But I hope it gives you the ability to visualize why the pointed tip is a bad idea and why a blunt tip, when it comes to our boats, makes for a better air terminal, a better lightning rod. I'm the Digital Mermaid. I am going to think now about what is going to be the next episode in this lightning series. If you like this kind of stuff, if you want to learn what I've learned as I try to share it, do the YouTube thingamajigs, and I will see you next time. Bye! When the ice crystal strikes the Graupel in the presence of supercooled water, the H2O splits into hydroxide. Is it hydroxide? Yeah. It's H plus protons. So positively charged protons is a hydrogen with no electron at all. And then you have OH negative, which carries the extra electron into the Graupel. The H plus, which recall, has a deficit of an electron, so it's a naked proton. So the H plus, which recall, is missing an electron, so it's a bare electron. Oh fuck, this is hard. I might put this into the end of the video because good lord. Oh, this is hard to keep straight of. Okay. I'm shaking my hands, but really I'm trying to loosen my brain.